Alright, these are some notes on section 4.1 to help you understand the material a little bit better. So 4.1 is talking about inverse functions, and an inverse function is when you switch the ordered pair of a regular function, you can create an inverse. Now it's only going to be a function if the inverse is also a function. So remember, it has to pass the vertical line test and the x's cannot repeat. So for example, I gave you this problem where I had -4 and -8. So I took the function 2x and I substituted in -4 and got -8. And then I took the function and I substituted in -1.5 and got -3. And then I substituted in 1 and got 2. So I ended up with this set of ordered pairs that represents this linear function. So then I have this other function 1/2 x. And I did the same thing. I substituted in -8 and got -4, and -3 and got -1.5. So you'll notice that the ordered pairs for each of these are completely reversed. So that tells me that these two functions are inverses of each other. So when I do the same thing for this function, now x squared is going to be a quadratic, right? So if you take a quadratic and you switch all the coordinates, you'll notice that you have 9, -3, and 1, -1. So what we have here is not a function, because you notice that the ones repeat and have different values, and the 9s are repeating. So this isn't actually a function. So a parabola would look something like this, and its inverse is going to look like this. So that's not a function, right? The inverse is not a function, so we call it an inverse relation. So everything that we're going to be doing in this chapter is dealing with inverse functions, so we're going to be manipulating to make them functions. Alright, so knowing that information, if I give you an ordered pair, or if I tell you this information, so if I say f of 2 is 12, that means I have the ordered pair 2, 12. So that means the inverse, that's the -1, would be 12, 2. So f inverse of 12 is 2. F of -2 is 16, so the inverse of 16 would be -2. Same thing, -3, 24, so f inverse of 24 is -3. So functions are inverses if and only if they're one-to-one functions. So we talked about one-to-one functions earlier, where we were talking about, like, for example, people and social security numbers are one-to-one functions. Every person has a unique social security number, and every social security number has a unique person. This is not one-to-one, so you'll notice that the original function is a function because each of the x values repeat. But you'll notice that every x value doesn't have a unique y value, because you'll notice here that this x value has a 1 also. So this one's not one-to-one, because if I switch all those coordinates, they don't become a function. So one-to-one functions. So the next thing we look at is if we graph these two functions. So we graph the original function, or the original graph, which is -1 and 1/2, 0, 1, 1, 2, 2, 4, and then we graph its inverse, which means we just switch all the coordinates. And you'll notice that you have the original function is coming up through here, and then the new function, the inverse function, is coming through here. So these have this line of symmetry as y equals x. So we know that the two functions are inverses if they have that line of symmetry. So leading to the next thing, so if I want to determine if two functions are inverses, then I'm going to use that y equals x line to determine by using composition of functions. So I'm going to take one of the functions and substitute it into the other one. So when I do that, you'll notice that f composed of g of x is equal to 2 times 1/2 x, which is x. So since the composition of functions is x, then that means that they are inverse functions. Here's another example. I took the 3x and I substituted it into the second equation. And when I do that, I end up with x. Or I could take the second function and plug it into the first one, And again, I end up with x. Now I got this by doing 3 times 1/3 and 3 times 2, and then that minus 6 is on the end. Okay, one more example, or two more examples. So if we look at this, again, let me move my mouse. We took the 2/3 x and we plugged it into the other function, and we ended up with this. So 3/2 times 2/3 is 1, 3/2 times 4 is 6, and then the minus 6, they cancel out. So yes, these are inverses also. So now here's an example that, depending on how you substitute it, you can make mistakes. It's almost easier in this case to substitute the first one into the second one. So when we do that, we end up with 1 over 3 and 3x, and that equals 1 over 9x. That's not x, so they're not inverses. Sometimes when we do it the other way, people mess up. So when you look at it this way, you have to say 3 times 1/3 x. The 3 and the 1/3 cancel out, but you're left with 1 over x, not just x. So no, those are not inverses of each other. So again, for all of these, we could substitute it into the calculator and look and see if that line y equals x is that line of symmetry, and we would usually not see that line of symmetry in there. Alright, so our next step. What if we want to find the inverse of a function? So to find the inverse, you're going to substitute y in for the f of x, and then you're going to interchange the x and the y, and then you're going to solve for y in terms of x, and then you're going to replace the y now with f of inverse x. So let's go through these steps. So I have this function, and I want to find its inverse. So I replace the f of x with y, and now I switch the x's and y's, and now I'm going to solve this problem for y. So I'm going to add the 6 to both sides. So I've got this written wrong. So I'm going to add the 6 to both sides, and then I'm going to multiply both sides by 3 to get rid of that 1/3. So I end up with this, and so that is my inverse function. So I could always verify this by putting those two graphs in my calculator. So if I put the first one in my calculator, I should see the line of symmetry that we have there is y equals x. So I'm going to put in the 1/3 x minus 6. And then in the second function, I'm going to put 3x plus 18. Okay, so here are my two functions, my two graphs. And if I could go ahead and graph them, but what I want to do is make one of my graphs y equals x, which is supposed to be my line of symmetry. So when I graph them, oops, let me get my Zoom 6 out there. Okay, so let's go back to our Zoom 6. So there's our first line, there's our second line. So if we look at this is the y of x line, and then these are the two graphs that we had. And you'll notice that they're symmetric about that y equals x line. So that tells us that we probably do have the correct inverse. Okay, so let's keep going. These are a little bit different. Each of these is a little bit different process. So on this one, what you'll notice here is you have the function and it's a rational expression. So y equals x minus 1 over x. Again, switch the x's and y's. And then I'm going to solve. So I'm going to cross multiply. Think of this as x over 1. And I'm going to cross multiply. And then remember your goal when you're trying to solve for y is to get all the y's on one side. So I'm going to move this y to the left. So I moved it over to the left. So now what I've got to do is figure out how to get the y's by themselves. And the only way to do that is to factor out the y. So I factored out the y and I'm left with x minus 1. And then I'm going to divide by the negative 1. So my inverse is negative 1 over x minus 1. And in that I have to say that x cannot equal 1. That's my restriction on my domain. So again, a lot of these that you have your rational expressions, you're going to have the same couple of steps. So you're going to go through and you're going to replace it, and then when you cross multiply, you're going to end up moving all the y's on one side and everything else onto the other side. And then you'll usually end up factoring out the y and then solving from that point. So here's another example, same type of problem. So we have y equals x over x minus 2, and then I replace the x's and y's. Now when I cross multiply this time, I have to do x times the whole binomial y minus 2. So when I distribute, I get xy minus 2x equals that y on the other side. So again, I've got to get the y's together. So what I decided to do was move that xy over to this side. So I subtracted the xy, and then I needed to get the y by itself again, so I have to factor it out, and I'm left with 1 minus x, and then equals the negative 2x, and then I'm going to divide. So my inverse, f inverse, is equal to negative 2x over 1 minus x, and x cannot equal 1 again. Alright, one more, a little bit more difficult, same idea. Okay, so I replaced the x's and the y's. Now I went ahead and skipped the first step and just jumped right to switching the x's and y's. Cross multiplied, so I ended up with x times this, which is xy plus 3x. And then I have the 2y minus 1 on the other side. So again, I've got to get the y's on one side. So I'm going to move this 2y to this side. So I'm going to move the 2y over here, and I'm going to move that 3x over there. So I'm going to subtract the 2y, and I'm going to subtract the 3x. Again, I've got to factor out that y, so I factored out the y, and I'm left with x minus 2. And then I divide. So my inverse, f inverse of x, equals negative 3x minus 1 over x minus 2, and x cannot equal 2. Okay, so our last two examples. So remember we talked about quadratics, right? So with a quadratic, you have to restrict your domain when you're doing this problem. So when you're looking at your graph, you aren't focusing on the entire graph, you're only focusing on one part of the graph. So what we're going to do is we're going to start off by following the same process that we did before to complete this, to find the inverse. So if you think about it, if I have a parabola, right, and let's just say I focus on one half of the parabola. So if I focus on this half of the parabola, if I flip that over a y equals x line, I'm going to end up with something that looks like that. And we've talked about this before. This is a square root function. So what we're going to end up with in this problem is basically a square root function. So here I have the problem, and I've gone ahead and I've switched the x's and y's. So now I want to solve for x. So what I'm solve for y. So what I'm going to do is I'm going to start off by moving that 2 to the other side and making it x minus 2. And then I'm going to complete the square. So remember, to complete the square, you do half of the middle term squared. So half of 6 is 3, 3 squared is 9. So I have to add 9 to both sides of this problem. So now I have x minus 2 plus 9 and y squared minus 6y plus 9. So now this reduces to x plus 7. And this is a trinomial squared, so it ends up with y minus 3 squared. So to solve this, I'm going to square root both sides. So when I square root both sides, I end up with this. Don't forget the plus or minus. And then I'm going to move that 3 over, so I get 3 plus or minus the square root of x plus 7. So here's where it comes in. So when I'm looking at my graph, okay, so I have to decide whether my answer is going to be 3 plus the square root of 7 or 3 minus the square root of 7. So the answer is actually going to be 3 plus, and let me talk to you about why. So here's our two graphs, and